Hi, my name is Noah Gift, and what I'm going to talk about today is Practical MLOps. And I'm going to go through the first chapter of Practical MLOps and walk you through what it is, what problems MLOps solves, what are the foundational components necessary to implement MLOps, and also step by step where are some code techniques that you can use to immediately get started. Really, MLOps is one of the hottest areas right now in software development because it takes something that was a little bit troubled, which is data science, and moves step by step and brings you through. Again, this is just the first chapter of the O'Reilly book, Practical MLOps, but let's go ahead and get started. I'm going to just cover some of the latest material that I created here in the Introduction to Machine Learning Operations book, and just scroll through and talk about a few key topics. So one of the things that is happening right now with machine learning engineering is that there's a need for people to get things into production. And that's really why machine learning engineering in particular is so important, and how many jobs are out there, and why MLOps is such an important topic. And here's a good example. If you look at LinkedIn, this was just in Q4 2020, that if you and do this research yourself, if you look through, the cloud itself has almost 200,000 jobs. I think it's probably going to be even more. And you can see AWS, Azure, GCP. These are all places where people are getting jobs or open jobs. Data engineer is very high, right? Companies are looking for people who know how to engineer things. Machine learning engineer as well. Data scientist is not actually a growing job title. Instead, the engineering aspects are growing. So data science itself is, I think, important, but the job itself as a job title is, I think, too vague. And that's why there's so much more demand for machine learning engineers and data engineers. And then if we scroll down here, let's talk about, what is machine learning operations. And I think one of the best questions is, why is not machine learning engineering 10 times faster? And I think that's really the key question, why people are interested in MLOps. And in particular, we can look at some of the things that can help you with MLOps and DevOps. One of them is continuous integration. And this is, I think, one of the most important aspects of getting started with software engineering, machine learning engineering, is that you must have the ability to automatically test your code. Second is continuous delivery. And so with continuous delivery, you're taking your code and you're pushing it into production automatically every time you make a change, that those infrastructure changes along with the source code has been delivered. And this is critical. If you don't have this capability, you're not going to be successful doing machine learning operations. Also, microservices, I think, are very critical as well, because a microservice allows you to wrap what you're building directly inside of the thing that is actually your project, and you don't have to have a bunch of extra code that is difficult to understand. Infrastructure as code as well is a very important topic, where you define everything that's happening in the cloud inside of a flat file. And there's several different flavors of this. If you're using AWS, they have something called CloudFormation and serverless application model. Let's take a look at this real quick. What is the serverless application model? It allows you to build serverless applications using their framework. And there's a whole bunch of examples here where you can use this, and it simplifies deployment, allows you to test your application locally. It builds on top of their CloudFormation utility. So this is a really important aspect of deploying things in a repeatable way, is using this infrastructure as code. Monitoring and instrumentation. So this is another critical component of a project that a lot of times, if you're in a university, maybe you're not getting a ton of exposure to. But imagine if you're driving a car and you can't see how fast you're going, or whether there's a problem with the vehicle because there's no dashboard. It would be terrifying, right? And the same thing, if you're deploying your code, you must have these dashboards, visualizations that see when was the last time you trained your model? Did for example the model have issues with performance? Do you need to deploy a new one? Really critical aspect of machine learning operations. Another one is effective technical communications, and really what's critical about this is that if you're not able to communicate what's happening to, let's say, the CEO of your company, then your project may not exist anymore because they cancel it. And so it's very important to have effective ways to communicate. Here's what we're solving. Here's the results of our project, and here's how it's impacted the business. And that's why I think a lot of data scientists have problems in their organization, is they're not clearly defining the value that they're bringing to an organization. I also think this is critical, and basically the ability to have effective technical project management is one of the most overlooked aspects of machine learning engineering. It's very easy to only want to do the technical things, but the hard work is actually getting things done in a timely manner, making sure that you're efficient, everybody's coordinated. Fortunately, you can do all of this in a very async and remote way, but this is one of the key problems, I think, that why data science projects often fail, is that there isn't effective technical project management. You don't necessarily need this to be a person, though. You can do this yourself because you can manage your own technical project management by, doing these techniques, creating tickets, creating an outline of what you're going to build week by week, and then maybe demoing that even asynchronously, creating little demo videos and putting it into some kind of a chat system. Okay, now let's talk about what I call the machine learning operations hierarchy of needs. There's a famous diagram in psychology about Maslow's hierarchy of needs, and what he talked about was that it's very difficult to get your full potential if you have no food, water, or sleep. Right? These are fundamental components to being a productive human being. Is you must have the basics like food, water, sleep. Safety is another one, right? If you're always concerned that people will hurt you, it's going to be very difficult to work on anything. You need to get somewhere safe. Relationships, if you have people that can mentor you and help you and work on things, that's very important. Esteem, another one, right? Once you have confidence in your ability, then you eventually can get to the point where you have your full potential, and the capability, your ultimate capability, is exposed once you're able to go through this pyramid. So likewise, if we think of machine learning engineering and ML ops, I think in terms of a hierarchy of needs, that if you're not able to do those DevOps techniques that I discussed earlier, so if you're not doing, for example, continuous integration, continuous delivery, you're not going to be successful in doing machine learning engineering. And I think this is not as known as it should be. You must have this in your project. Second is this concept of data automation. So are you able to automate the collection of data, the processing of data, the cleaning of data? If your data is not automated, how could you possibly build something that works repeatedly? You might get lucky, right? If one time you build a model, the data was clean, but then what about the next time you need to build a model? You must have something where the data is automated. And this is very similar to if you think about clean water, right? How could you possibly build a city if all the water that comes into the city is polluted? Everyone's constantly getting sick. So how could you have a city that's effective? Same as the data, right? The data must be clean, it must be automated, and it must be sanitized in usable in a form that you can do machine learning with it. Now, likewise, the platform automation, I think, is a component that builds on top of this. And this is where things like AWS SageMaker, Google's Vertex AI, Microsoft Azure's machine learning studio come into play, is why would you be doing things manually if there's automated tools that figure out hyperparameter optimization and can version models for you? It's really a waste of time to do things that machines can do for you. Finally, at the very top, you have MLOps, and you're able to produce reliable machine learning applications. So this is my opinion of what the ML hierarchy of needs is. And so one of the things that is a good thing to think about when you're starting in building a machine learning application is, and you want to get started with the first layer, which is the DevOps layer, is to have a scaffolding for your project. And most machine learning projects are in Python. I mean, people are doing things in other languages like R or Go or .NET, but in general, most people are using Python. And this is my opinion when you're building a project, is that it's important to have this concept of a scaffold. And what's important about this scaffold here is that it gives you a structure that makes it easy to understand what's going on. And if you create a makefile, the makefile can be the component of your project where it's a set of instructions like a recipe. And then your requirements file is where you would have your packages. You would have your source code. Maybe it's the web code that goes, the microservice that does the inference. You have some kind of a test file. And then you also create a virtual environment, and that would protect your project so that it doesn't get confused with other projects on your computer. And so really these are maybe the basics. And if you want to see an example of this, if I go to this project here and we go to, this here, you can see this is an example in this repository, the scaffolding. There's a makefile, there's a requirements file. Let's take a look at these. Here's an example of the makefile that it's really just a set of instructions. It says, here's how I install my code. Here's how I test my code. Here's how I format my code. Here's how I lint the code. So it checks for syntax errors. And then I could even do them all at the same time. And these set of instructions will get run later by the build system. And the build system, in fact, we can see this if we click on this icon right here, actions. And if you go to actions, and if I just do a change to the repository, we can see a trigger and watch it work. So I'm going to go to this repository here, and I will click on the README file. And if I just add maybe a little note here, let's do a note that says trigger build like this, and I can commit that change. As soon as I commit this change, if we click on actions, notice that it's now redeploying my project or rerunning whatever set of instructions I have. If I click on it, we can see that in fact it's going to do two things. It's actually got two jobs. One is it builds a Docker container. The other one is it runs a set of instructions. And these are all coming from the makefile. So it's installing the dependencies. That's one of the things I did in the makefile. After it's done installing the software, it will go through and it will lint the project by checking the syntax of the Python code automatically. Once that's done, the next thing that it'll do is it will go through and it'll test the code. So here we go. Now it's on the lint step. There we go. It's running this command pylint, checking the machine learning code, the command line tool code, some other utilities. That was successful. Then it goes through and it tests with PyTest, and then it formats the code as well. So it makes sure that the code looks good and cleans it up. And then now my job is successful. So what's so critical about this is that if you were doing this manually, every single time you deployed your code, it would be maybe 10 to 100 times slower because you can't do things as efficiently as a machine. And that's really the concept of continuous integration, is that you're automatically testing your code every single time you make a change. And that's really the basis or the foundation for a machine learning project. And so this is where the scaffolding comes in, is that this is really the structure that sets all this stuff up in motion so that you can do continuous integration. As I mentioned before, the makefile is the recipe for the system. That's really, what it's useful for. And you can see that, typically this is what I do. I say make install, make lint, and make test, install the packages, check for syntax, and then run some tests that verify that my code works. You can see what that looks like. The requirements file is also just a convention that you'll see a lot in code. And this is where you would put in the packages, and you can even put in specific versions, which is a very good idea in a production environment, is to specifically version the packages that you use so that you know that it's been tested and validated with a very specific version of that package. The source code and the test file, you can see what they look like. Here's a very simple example, right, of I have a function that kind of adds things together. But then if I want to add a test, you can see here, this is the test file. Is all I would do is that I would say from this other function, import it, and this test framework called PyTest, it makes it very simple, right? I just add an assert statement, and with that assert statement, that's all that's necessary to create the test, and then we can validate all the functions. And really, it's a very efficient way to get some quality control on your project. And this one is also, I think, very confusing to people, the local virtual environment when you're building things. And why I think it's so critical is that because Python itself is an interpreted language, what's important to know is that it can pull libraries from the entire operating system, and those libraries could conflict with what you're trying to build. And so what a virtual environment does is it isolates your environment to a directory, and then you can control what's installed in your project. So in my opinion, it's critical to use some tool like this, and Python virtual environments are probably one of the tools that's most commonly used. And if we scroll down here, here's another example of a tool that I think can be helpful, is something called GitHub Codespaces. And the reason I like these cloud-based development environments is that I think it's going to be the future of software engineering, because why would you want to maintain your desktop computer? Why not just use a web browser somewhere and build all of your software inside of there? And so let's take a look at how that would work. If we go back to this project here, and if I go back to here and click on your code space right here, that I can actually go to this project, this Python MLOps cookbook, and you can add any repo you want here, right? But I can actually launch it. I can say open in browser, and what it'll do is it will actually launch a full development environment for me. And again, because they're maintaining it, it reduces the complexity of me needing to work with software. It's going to be powerful as well, so it's going to have good CPU and memory resources. And even better is that I could not even need to own a computer anymore, right? I could use a very inexpensive computer and develop software directly by using somebody else's resources. I could go to the library, or I could go to my university, and I could actually start writing code anywhere. I don't have to even bring my laptop. As long as there's a terminal somewhere that can spawn a web browser, I can write code. So I think this is a very powerful feature that is going to be more and more adopted. And then again, if we go through here and I let's take a look at how this would work. If I say let's look and see if I created a virtual environment here that we could use. I think I see one potentially. It doesn't matter. I can create my own virtual environment. So if I say Python, or I say virtual environments, and we'll say cookbook, like that. there's two ways to invoke it, either virtual environment or Python 3-m virtual environment. This particular framework or setup requires the virtual environment tool. And if I then say source, and I go through here, I can do bin activate, and then notice how this changes over here. And now I can say which Python, and see it's keeping all of my code in this one directory, all of my libraries, all of my environment. So that's why it's powerful. And then what we can do is we can say make install like that, and I can install my packages into that virtual environment. And notice that it's putting all the code in there. And then again, if we look at this make file here, you can see that I can install my code, test my code, format my code, lint my code. And so we can go through here and we can say make lint like this. And this will make sure that my code is able to be successfully linted. There we go, 10 out of 10. And then if I say make test, same thing. We can see that all of my code is able to be tested. Although this is something, I must have some error. I don't know what that module is, but I would have to later, debug it and figure out, why there's a problem with this. But in general, I lean towards building code in these environments because they're so convenient to kind of work with things. And I can also start invoking my code as well. I think I have a command line tool here. I can do this, right? I can start, building things and testing it out, figuring out what bugs exist, all by working in somebody else's cloud-based environment. So the next thing that I'll bring up here is that when you're hooking things up to continuous integration, that one of the tools I think that's most commonly used is a tool called GitHub Actions. And notice here that inside of your project, you need to have a YAML file that is in a directory called GitHub and workflows. So if we go back to this project here, the reason why all of this works is I have a directory called .github and workflows, and I created a YAML file here. So if we click on this, you can see that really what this is it's also a set of instructions. So we're telling the automation system that I want to run in a Ubuntu container, and I want you to let me use Python 3.8. That's a version of Python. I also then want to run each of these makefile steps. So very convenient and very clear. You can look at this and you're just telling the machine what to do. Also, notice here I could do fancier things, like I could automatically build a container programmatically every time I make changes. Whatever machine learning code I have or source code could be put inside of this container as well. And so there's some really powerful things you can do with GitHub Actions. And my recommendation is one of the best places to start for continuous integration. If we click on this actions here, one of the things you can also do is look at the workflows and notice that they have many different example workflows for you, from deploying Node.js to deploying the Alley Cloud to deploying to Amazon ECS. Let's take a look at this one real quick. Deploy to Alley Cloud. If we set this up, notice here that it's going to give you an example of how to use an ACR repository, Alibaba Cloud Container Service for Kubernetes. You can set up a cluster. All these things are all set up for you, and you just need to tweak it a little bit and to deploy your application. So I really think this is a recommended way for most people to very, very quickly get up to date with continuous integration, continuous delivery, which is a DevOps principle, right? This is the foundation. Okay, let's take a look here at this concept of continuous delivery. I talked about it a little bit, but let's get into a little bit more detail. So in general, with continuous delivery, the concept is that you have your code in a source code repository like GitHub or GitLab, and every time you make a change to that repository, like we just went through, that a change will then be triggered in a particular branch. In the real world, you have more than one branch. So the master branch or the development branch or whatever you want to call that branch will be automatically deployed to a production environment every time you make a change. But more likely, if you're working in a corporation, that you'll have other branches and you'll merge your code from the main branch into the staging branch into the production branch, and then from there, each of those environments will actually get code. And so in the example of a production environment, one of the things that would happen is that this would be, let's say, the real world application. You would merge from the main to the staging to the production, and then it would automatically deploy that and test it out. So that's really the concept of continuous integration, continuous delivery. Now, let's also talk a little bit about this concept of operationalizing data, or data operations and data engineering. And there's a lot of different tools that are available, from commercial tools to open source tools. Apache Airflow is one example. This was developed by Airbnb and open source. Other tools that are cloud-based include things like, AWS Data Pipeline, AWS Glue. And really what do these things do is, a lot of times they're allowing you to do extract, load, transform. So they pull the data from somewhere, load it into some location, do some kind of manipulation, and then run that periodically. Another one is Athena. I think for big data sets, many times people care about Athena and QuickSight, and those can query and visualize the data. And so here's an example of a periodic collection of jobs here. So you would put the data in a data lake, and the data lake itself is the reason why people use a data lake is that it is a resource that has essentially infinite compute and infinite storage. And so if you keep everything inside of there, you have appropriate security, you have some kind of a structure, then you can periodically move things into this location. For Amazon, their data lake is called S3 with their object storage system. Every cloud platform has some concept like this. And what would happen is you could start to build out the features for your model programmatically, right? So as the data gets collected, maybe the features get cleaned up, maybe the data is normalized, or there's some kind of a transformation that occurs and missing data is removed. And then you now have very high quality features available for you to build things. So again, it's a lot like a water system, right? That, water sanitation goes through several different processes. And then when you go to your house, you're able to open up the tap and you can use water for tea, you can use water for cooking, you can use water for, watering your plants. There's lots of different locations that you can pull from that have high quality water. Same as with Feature Store. Once you've sanitized things, you've cleaned it up, you can then use it for exploring what features to deploy in a model. You can also deploy maybe dashboards that show different projects or different things. And then later you could do big data processing. If it's a big data problem, it doesn't have to be a big data problem. And then you could also do machine learning, right? So you could create models, version those models, try those out. So there's not just machine learning that you're doing when you have the data operations. You also could be doing other things, like, for example, a big data job could just be count how many people visited our website in the last 10 years. Right, that's a big data problem that has nothing to do with machine learning, but you would need a data lake if you had a large enough data set in order to get that metric, and then potentially you'd want to put it into a dashboard so that the executives in the company could do something with that data. So again, with a dedicated job title like data engineer, you could spend a lot of your time doing things like periodic collection of data. You could process the streaming data. You could do serverless and event-driven data. You could do big data jobs. You could also do data and model versioning for ML engineering tasks. Now, another one that I brought up earlier that I think is not very commonly talked about, that's very, very important, is this concept of platform automation. And so again, if you've already gone through and you have DevOps working, continuous integration, continuous deployment, you then next have already built the feature store and ways that you can keep track of your data in a proper way. Then the next thing, make this a little bit smaller. the next thing to be aware of is this, and let's see if we can make this image a little bit bigger. Is that imagine building something like this yourself. Even if you have a very strong software engineering background, this would be very difficult to architect a system like this completely from scratch. Let's look at a data science workflow. So first, you go through here and you ingest the data, you retrieve it from S3, you then perform some kind of exploratory data analysis, clean it, visualize it, scale the data. Next, you would go through and create some kind of a modeling. So you would create a prediction model. And then finally, you go through and build out a conclusion. Well, one of the issues here is that that process, it seems simple, but behind the scenes, there's a lot of different resources that get provisioned up and down, and they're managed. And if you use a platform like, for example, AWS Sagemaker, it will handle all of those things for you. So a good example would be, again, you start with doing something with a Jupyter notebook inside of the Amazon platform. And then what happens is that you need to communicate back and forth with the data lake, which is S3. So all of your training data needs to go back and forth with this notebook. So it's very good that this framework is here to kind of facilitate that communication. Next, though, you might need to clean the data up, do some kind of exploratory data analysis, drop missing values, do histogram, maybe do some kind of scaling. Well, that exploratory data analysis here also may require spinning up other resources. Finally, let's say you're ready to go. You want to then build out maybe some kind of a clustering model. Well, you might have to first provision a bunch of different virtual machines. And so you could do a distributed training using, let's say, principal component analysis to limit the amount of features you're dealing with. And then that itself could, again, provision 3 nodes or 10 nodes or 20 nodes. And then when it's done, it writes the data back to the S3 bucket. And so now that initial model is stored in here. But how do you use the model? Well, in order to use the model, you'll then have to provision a production endpoint. And so that production endpoint will be able to communicate down to the S3 location, distribute an API, and then that may spin up itself 3 different nodes. And so if other people in your company need to use your principal component analysis model, they will then need to talk to that API. And if it gets very busy, the elasticity may need to scale. And then instead of being 3 nodes, there could be 6 nodes or there could be 10 nodes. So this is really critical that you have a system that's already designed to handle this. But as you may know, in many clustering models, that you want to actually first do principal component analysis and then do something like k-means clustering on top of the other model. So now you have to train another model. And this one is the k-means clustering model. It goes through, it puts this inside of S3 again, and now you have a second endpoint that allows you to do the clustering. So really, in a nutshell, even though it seems simple in the data science workflow, you ingest data, you do exploratory data analysis, you do modeling, and then you come up with a conclusion. In practice, by using a platform, and this is AWS's platform, it will automate all these things that are very, very challenging, and that really it could take you a week or 2 weeks or a month to do something like this yourself, or you just click a button and it does it all automatically for you. So this is why the platform automation is so critical. when you're building real world machine learning applications. So, now we get to the point of, what is MLOps? And as I mentioned, really it's assuming that you've done DevOps. It's assuming you've done data automation. It's assuming you've done platform automation. Once you've got that, then we're at the point where we can start to do high level things like, for example, I want to monitor what's happening in production, and I want to train and retrain the model back and forth, and then deploy new versions of that model and then audit the trail. So what's a good example of this in the real world? One really good example of this would be self-driving cars. And this has gotten a lot of press recently because I think there are some concerns about the safety of self-driving cars. Are they really good enough? And I think there's some real concerns. I personally am very concerned about the safety of self-driving cars. But this is where you could start to look into what's happening, right? You could monitor what are the results of the model when it's in production, so it's driving on the road. What happens? Is it successful? Is it making the good decisions that we want? If it's not, maybe we need to, or even if it is, we need to constantly train it and retrain it with new data, and then deploy the new version, and then audit what happens and see the feedback loop. So this is the part where it's really important to have automation. How could you possibly do this if you don't have all those other things automated? And so you must have really, in order to do MLOps, a full comprehensive automation so that you can get to the part where something like a self-driving car, you can look at it and say, okay, now we can focus on whether the car itself is really doing what we want it to do, and then constantly give it more and more information and feedback. So again, the idea here is to create and retrain models with a reusable ML pipeline. That's really the concept. Continuous delivery of ML models, constantly giving updates, right? You see this with phones, right? They're constantly getting new updates or different systems. We have an audit trail, and I think this is really important for many different reasons. So here's a good example, and this is something that I, again, have some concerns with self-driving cars, is imagine if the self-driving car is around for 10 years and it looks like everything is going successfully, but what happens if someone has been secretly poisoning the data, right? So they know that the vehicles are trained on the public roads, and someone has been sabotaging slowly the self-driving car with secret data that causes it to behave a little bit strange. And then they've poisoned it enough that when they're ready, they release some signal, and then all the cars crash at the same time, right? How would you ever know what it was that caused that model to behave strangely and crash unless you had an audit trail that looks at every single change that ever occurred, and you could go back in time and figure out when the data was poisoned, where it was given training data that made it behave in an unpredictable manner. So I think this is very, very important in a real world solution, is to know at what data point you're training your model and what the actions were, so you can always go back in time. If you never kept track of the audit trail of each different incremental change, it's possible you'd have to throw the whole thing out because you don't know when the bad change was made that corrupted your machine learning model. And then this is another one that comes up a lot, is this concept of data drift, right? When you're building machine learning models. And in particular with data drift, what it means is that, did all the underlying data change very, a high level of the data? So again, with self-driving car, let's say that you've collected 100 terabytes of data 6 months ago, but now the data set is 200 terabytes. Well, you have a 50% data drift. You have 50% change here. And so what you need to do is make sure that, you've doubled 100%. You doubled the change here, and you should retrigger potentially a retraining of the model so that you're able to alert when the data has changed so much, because it may be the model may not behave the way you expect it to behave if it's collected all this new data. And again, this could be the part where you see that maybe there was a bad change that was made to it. And so again, a good example of what this would look like would be use a platform which automates a lot of the aspects of it. You have a model. The model can be exposed via API. It could be exposed via container. You could expose it via a native mobile application. Maybe you could expose it via JavaScript, an edge device. And then in particular, with a cloud platform, you could use AutoML as well, and that AutoML could even deploy to all these different targets. And this is something I've played around with a lot, and I think is very useful, is this concept of the platform itself, like the Google Cloud has this Vertex AI. Once you've trained it, you can export it as a edge-based model that can go on a device. It can go to JavaScript. It can go into maybe iOS. It can go into container, or it can go to, again, like a physical device. That these are all things that are artifacts that can be created once you've been able to successfully build that automation. So this is my opinion of what MLOps is that really it's 25% DevOps, it's 25% the data, it's 25% the model, and it's 25% the business case. So I think if you look at self-driving cars, it's a very good example of this, is that you must have automation to test your code and deploy it, right? Like how could you possibly not have that? Same as if the data itself that's working towards the self-driving cars is not cleaned and processed, how could you possibly build a model? Likewise, once you have the automation built with a platform, then the platform itself will help you create maybe 10, 100, 1,000 models a day. But that's not enough, because even with all three of these, that what happens if the business case and there was an example of this recently with Tesla, where there was a vehicle that took a left turn in front of a Tesla, and the Tesla followed it and then hit it from behind, and the vehicle flipped. And so in that particular situation, you could say, well, what is the business case of our problem? Let's look into this. Let's dig into the details about this business case. Is it really the business case that we want to solve or not? So in my opinion, you need all of four of these constantly working together in order to do successful MLOps. Okay, so there's a few things that I'll mention here that I think are very helpful in getting this lesson finalized. And in particular, I would say that being able to create a new GitHub repository with linting, makefile, all that is very important. Using GitHub Actions as well, I think, is a really critical tool to be able to use to make sure that you understand this concept. Looking into these cloud native build servers, I think if you have access to a free account with AWS or Google or Azure, look at what they build on their platforms. And this would be a good way to understand how it would work with something like Sagemaker. Another thing to follow up on would be how to containerize a GitHub project by integrating a Docker file. Also, how to create a simple load test for your application. Doing something like Locus or Loader AI. These are all good introductory things to get you more and more familiar with. And then in terms of critical thinking, I think these are good things to maybe ask teammates or people in your class about, or think about yourself. Why do people use continuous integration? What is the big solution? Why is continuous integration an essential part of software? Why are clouds the ideal target for analytics applications, for data engineering, DataOps? Why does deep learning benefit from the cloud? And could you even do deep learning if you don't have cloud computing, and then explain what MLOps is and how it can enhance a machine learning engineer. So just to touch on a few of these real quick, I think one of the ones that I'll talk about real quick is this concept of deep learning. Is it even possible to do deep learning if you're not using cloud computing? I would say very difficult to do deep learning without cloud computing, because it requires the ability to train models on very large data sets, and also to use these high computational power. It doesn't mean that people couldn't build their own data center, but I think most people, if they want to use deep learning, would more than likely need to use expensive GPUs and expensive storage, and most likely that's going to be in the cloud.